This video file was recorded in Sabunja University during recitations for the CS204-Advanced Programming course as it was given in the spring semester of 2017.
Okay, let's continue with something else. Namely, have you ever thought that when we have been dealing with numbers from our childhood, have you ever thought, why do we use 10 digits? Namely, from 0 to 9, we have 10 digits. Why don't we use less or more than that? Let me write some numbers. So we call our system the decimal one. We use from 0 to 9. These are the digits that we use. Let me write them, some of them. So 0, 1, 2, 3, 4, so I can count, as you can see. 5, 6, 7, 8, 9. Now I'm finished. I've used all of my 10 digits. What I'm going to do? Well, I will reserve another place. I'll put it to 1. And the leftmost digit, the less significant one, I will put it to 0. Then I'll continue, 11, and so on. Okay? This is the decimal system. Unfortunately, or fortunately for us, the computers don't understand the decimal system. What they understand are binaries, 0 and 1. Why is that the case? You have heard about magnetic tapes. You have heard about diskettes that used to be used like 15, 20 years ago. Well, they use magnetic poles, north or south. And we have only two states. Some transistors, some electronic parts, and you're going to see them maybe, if you are CS or mechatronic guys, they use current. If there's current, we say it's 0. Otherwise, we say 1. So we have only two states, 0 and 1. This is how computer works. And not only, everything basically in computers is saved in terms of binary numbers. Even the audio that you record, even the color that you show on your screen. Everything is bits. So, we have another system which is called binary, and we have two digits to represent it called bits, 0 and 1. Have you ever seen binary numbers before in high school or not? Yes, okay, very easy then. So, how do you represent 0? Very easy, it's 0. 1 is 1. Afterwards, I go 1, 0, 1, 1, 1, 2, yes? 1, 2. 1, 0, 0. And I have 1, 0, 1. 1, 1, 0. 1, 1, 1. Then I would say 1000, but this is 8. This is how I write 8. In binary system. 101, 1001, 10, 10. 1011, and so on. Okay, so this is the binary system. Let me give you a number. Let's say I'm giving 3679. And how do I represent it in terms of powers? Well, always this guy is 10 to the power of 0. Because we're using 10 digits, this is 10 to the power of 0. This one is 10 to the power of 1. 10 to the power of 2, 10 to the power of 3. So I have 3 multiplied to 2, 10 to the power of 3, plus 6 multiplied by 10 to the power of 2, plus 7 multiplied by 10 to the power of 1, plus 9 multiplied to 10 to the power of 0, which is 1. And the reason why I wrote this is because of this formula. Basically, I can write any number in this form. DI is for decimal, meaning I have numbers 0 to 9, multiplied by 10 to the power of I, where I is the corresponding place. We start from 0. So here, this is 0, 1, 2, 3. This is the I. So far, so good. I know it's easy. And I'm happy that it is easy for you. So this is for decimal numbers. Let's see for binary numbers. What do we get? If you want to convert, basically this is conversion. Conversion from what? From binary to decimal. How am I going to do that? Let me write a number that we, from here, let's say it's 1011. I know that it is 11. But how am I going to get this 11? So I have 1011. How am I going to get 11? Can you tell me? We're going to use the same method here. Since we have 10 numbers, I have 10 to the 0 here. Only when those 10 combinations are filled, I go increment this guy. That's why I have 10 to the power of 1. Only when those two guys are filled, which is 100 combinations, I go here. That's why I have 10 to the power of 2, which is 100. Only when those three guys are filled, I go and increment this guy. Those guys make 1,000 combinations. That's why I have 10 to the power of 3. But why I have 10? Because I have 10 digits, 0 to 9. What about binary numbers? Yes, I have here 2 to the 0 for this one. This is 2 to the 1, 2 to the 2, 2 to the 4. Sorry, 2 to the 3. Okay, which is actually this guy is equal to 1. This guy is equal to 2. This guy is equal to 4. This guy is equal to 8. Okay, so how am I going to write this? 1, 2, multiplied by 2 to the power of 0 plus 1, multiplied by 2 to the power of 1, plus 0 multiplied by 2 to the power of 2, plus 1 multiplied to 2 to the power of 3. But I'm going to raise the powers now. Where is my eraser? I don't see it. Do you see it? It's there. Okay. Instead of powers, I'm going to write here 1, 2, 4, 8. One way to very easily find the corresponding decimal representation of a binary representation is just to count the ones with the corresponding value they have. So if we are talking about the unit, it's 1. Okay, 2 to the power of 0 is 1. Plus 2, because I have 1 multiplied by 2 is 2. 0 is not counted, plus 8. So 8 plus 2 is how much? 10. Plus 1, it's 11. In those corresponding places I have 1's. That's why I just count those powers, and this is it. Now this is what I get from here. 10 to the power of 0 is 1, plus 2, plus, this is 0, I'm not going to write it, plus 8. This is how I get it. The formula from converting from binary to decimal is this one. So this is the formula. This is the formula for conversion. So it's the summation of bi multiplied by 2 to the power of I. Okay? Is this clear? I think, is this clear or not? I mean, the best way to convert a binary to decimal is by seeing those numbers here. 1, 2, 4, 8, then we continue 16, 32, and so on. We don't need anything else. With those numbers here, you can come up with any number. For instance, I want to represent 7. How am I going to do that? With adding those numbers, 1, 2, 4, 8, 7, 8, 16. 4 plus 2 plus 1, it's 7. So I should have 1, 1, 1 here. If we see here, 7 is 1, 1, 1. 1 plus 2 plus 4. If I want to represent, let's say, 4, very easy. I have 4 here. So I should have 1, 0, 0, 1, 0, 0. Okay. For 9, I should have 8 plus 1 is 9, which is 1, 0, 0, 1. So it's 1, 0, 0, 1. This is the best way to represent numbers, to convert numbers from binary to decimal. So far, so good. Of course, if you have any question, please stop me and ask me. Now, how can we do the opposite? How can I convert a number from decimal to binary? Any idea? Can someone do that? Please don't tell me the calculator does it, because I want you to do it with your hands. Let me give you an example how it is done, and we will not have any problem about that. So, I'm going to show the examples here that we should solve. These are the examples. Our first task will be to convert 120 to binary. So, how we will do that? I write 120 here. Then since I'm converting to binary, I have 2 digits. I'm dividing 120. Any question? Okay. So, first question, 120 to binary. When I divide 120 with 2, what is the remainder? The quotient and the remainder. Yes, it's 0, you can say. So I'm writing 0 here, and I have 60 here. Again, I divide 60 by 2. I get 30, the remainder is 0. I divide 30 by 2, I get 15, and the remainder is 0. I divide 15 by 2, what do I get? The integer is what? 7 and 1. If I divide 7 by 2, what do I get? 3 and 1. I divide 3 by 2, what do I get? 1 and 1. If I divide 1 by 2, I get 0 and 1. Our number will be this one. Starting from here, this is the most significant bit to the least significant bit. So 120 converted to decimal, this is how you write it usually, 10, is equal to 1, 1, 1, 1, 0, 0, 0 in binary. If you don't trust me, you can go 1 plus 2 plus 4 plus this is 8, this is 16, this is 32, this is 64. Add those numbers, you'll get 120, or even better, since we'll live at the age of technology, that as the calculator proved that this is true, so I have 120, and I'm trying to convert it to binary. You can do it by setting the view to be programmer. So this is 1, 1, 1, 1, 0, 0, 0. 1, 1, 1, 1, 0, 0, 0. This is it. Okay. Did you know this before or no? Oh, kind of, yes. Very nice. Let's go with this guy now. Can you tell me what is the corresponding representation of this guy to decimal? Let's do it in terms of power. So we have 1 here, 2, 4, 8. They're not counted. 16. 1 and 16 is how much? 17. We have 32. 17 plus 32 is how much? And again plus 64, which is how much? Come on. You should give the answer. Okay, you can count.
130.
Exactly. So I'm going to erase this, we don't need it. The number, we did our first question, the second question is this one. 0, 1, 1, 1, 0, 0, 0, 1. Okay? So we have here 1, 2, 4, 8, 16, 32, 64. When we add those ones, 64, which is equal to 64 plus, this is in binary, in decimal is 64 plus 32 plus 16 plus 1. In decimal, this is 113. So we know how to convert numbers now, from binary to decimal and vice versa. This is awesome. I'll give you like 30 seconds and think about this. We saw how we can represent numbers in binary in this manner. Let me put, of course, if I put zeros in the beginning, it doesn't matter. If I say I'm 29 years old, if I say I'm 0029, it's the same. But what about negative numbers? So remember, the computer, when it saves a number, let's say, well, we're talking about numbers. If it wants to save 8, it saves it like this, 1000. This is 1 bit, and it puts it in a flip-flop or transistor. You will see what it is about later on. Because it can distinguish only if there is current, there is no current. If there is current, it's 1, otherwise it's 0. Okay? So how we can represent negative numbers in this manner? With? Did you attend the lectures? Yeah. No. What do you mean by sign bit? Initially you have plus or minus. If it's 0, it's plus. Otherwise it's minus. Very nice. So it should not come as a surprise to you that the first programmer in the world was a female. She was a woman. Okay? Did you know that or no? No. Her name was Ada. And if you have heard about George Gordon Byron, he's a famous English writer. And this programmer was the daughter of that guy. And if you have heard about the Ada programming language, it is done to honor that particular female, okay? So, even your friend didn't know that, but she came out with a way how to represent numbers. She said in the beginning, I put another bit, 0 if it's a positive number, 1 if it's negative, which makes sense. So let's go and do that stuff here. Shame on you guys. Yeah, shame on you. You can lower your head like this, you're right. So, this is the way we might assume the computers are representing the numbers. Sign and magnitude. 0 means it's positive. 1 means it's negative. For the most significant bit, MSB, most of the significant is the leftmost bit. Okay, so in the sign magnitude representation, what does this mean? Is this positive or negative? We check this bit here. It's positive. That's why we can write it plus 0. What about this one? Yeah, it's positive because of this 0. Plus 1. So we have plus 2. It's called sign and magnitude because you take the bit as the sign and the rest is the magnitude. So this is plus 3. What about this one? Because of 1, it's negative. We write minus 0. This guy is what? Minus 1. This guy is minus 2, so minus 2, minus 3, minus 4, minus 5, minus 6, and so on. Is there any problem with this guy? 1, 2, 3, 4, 5. No, everything is okay. You're right. That's why I should write it, very nice remark, okay? That's why I should write it like this. So if I have a negative number, if I want to expand those guys, those are 3 bits. If I want to expand them to be 4 bits, I just put, if they're positive, I just put as many zeros as I want at the beginning. If I want to make them 32 bits, very nice remark, I should have 32 zeros, or namely 31 zeros, okay? But if we are dealing with negative numbers, then we should add 1s at the beginning, like it is the case here. Okay? Very nice. So the one problem is usually the computers have a limited size to represent the numbers, let's say 32 bits, 64 bits. And we will see a lot of problems with this representation. We're going to solve many examples, and I warn you they're going to be part of your finals for sure. Maybe your homeworks as well. But there's another problem here. Yeah, you might say, okay, so what? Plus 0 minus 0 is the same. I don't care if I represent the same thing with two different bit representations. Those two are different, by the way. Which is that like this. Okay, but not this one. Yeah, you might be right, but you're not a good engineer if you do the same thing twice. That's why we come with another way of representing binary numbers, which is called 1's complement. Again, for the 1's complement, if I have 0 in the beginning, so this is the binary. If I have 0 in the beginning, it means plus. If I have 1 in the beginning, and the beginning I mean the most significant bit, the bit which is at the most left bit, then it's a negative number. What is the value of that negative number? So sign and magnitude and 1's complement are the same when we are dealing with positive numbers. So basically this representation 0, 0, 0 is going to be again 0. This is again 1. This is again 2. This is again 3. But what about this one here? 1, 0, 0, 0. This is how it works. If I have a negative number, then I'm complementing it. That's why it's called 1's complement. Complement means if it's 0, make it 1. If it's 1, make it 0. This is true for the old bit string. So here I have 1, 0, 0. It means it's a negative number. But what is its value? I just complement it, and I switch the values of 0s and 1s. So 1 becomes 0, 0 becomes 1. What is this value if it was a positive? This is 3. But because this is negative, we are writing, so this is minus 3. What about this one? 1, 0, 1. I don't know. Let me check it. So this is for the 1's. 1, 0, 1. 0, 1, 0. This is minus 2. What about this one? 1, 1, 0. Complement, this is 0, 0, 1. So this is minus 1. What about this one? 1, 1, 1. Complement, this is 0, 0, 0. Minus 0, yeah, you might say it. I'm not going to go furthermore. Let's stop here. This is how we represent numbers in 1's complement. You might say why I'm complicating my job, because again we have two zeros. Minus 0 and 0 is the same. Well, there's another representation which is called 2's complement, and this is the way that actually our computers now they represent the numbers. For zeros, it's again positive. For 1, it means we are dealing with negative numbers. So sign magnitude, 1's complement, 2's complement, 2's complement are the same when we are dealing with 0. So if we have 0, 0, 0, whatever, we have 0, 1, 2, 3. But the problems come here. If we have 100 with 2's complement, this is how it works. We complement the number. So 100 is going to be complemented to 0, 1, 1, 1. And we add 1. Okay, so we do something like this. Plus 1. Which is 0, 1, 1 plus 1. Which is, let me write it here. How much is this? 100. And 100 is how much? It's 4. That's why we have minus 4 here. So this is the difference between 1's and 2's complement. Now let's go with 101. If we have 101, this is how we convert it. We have 0, 1, 0 plus 1, which is 0, 1, 1. This is minus 3. 1, 1, 0 plus 1. We have 0, 0, 1 plus 1. How much is this? 0, 1, 0. This is minus 2. What about this one? 1, 1, 1 plus 1 is going to be 0, 0, 0 plus 1. This is 1. And this is going to be minus 1. Do we have two zeros here? No. We have only one. That's why we have, you see, 4 negative numbers, 3 positive numbers. We can do it if we are dealing only with how many bits? 3 bits. So with 3 bits, we have, of course, 8 combinations. And the range is from minus 4 to 3. Okay, the range is from minus 4 to 3 with 2's complement. So which one is better to use? 1's complement or 2's complement? It's 2's complement, but not only because we don't have 2 representations of 0. There's another reason, very important reason, and we will see it in a while. Okay. So we saw that one problem is, I told you, I'm using, for the time being, 3 bits here. But usually, at least that the data types used is 8 bits, which is 1 byte. So let me see an example here. Actually, it's going to be the third example. I should represent 35 and minus 60, but I don't have time about that. That's why I'm going to represent 110 and 80 because we are going to need it for the following example. So, our first job is the following. This is the third and the fourth task for today. First, I want to represent 110 in all of those representations. So 110 decimal is how much? In sign and magnitude, it's how much? You know how we can do that? Yes, we know how we can do that. Is this a positive number? It is a positive number. That's why I'm going to use the calculator here to do that. We already saw it with the remaining stuff. So I have 110. In binary, this guy is, in sign and magnitude, it's 110110. We have 1, 2, 3, 4, 5, 6, 7. We are going to make it 8 bits. Let's assume that we assign 8 bits to represent the numbers. Since this is a positive number, what is going to be the corresponding 1's and 2's complement? Any idea? Come on. So, first and 2's complement. So for sign and magnitude, this 0 means it's positive. 110, 1110, because you got it. It means 110. Okay, for 1's and 2's, how is it going to be? We are going to change zeros and 1's? Yes or no? Any idea? Come on. So what did I tell you? What did I tell you? Do you see any difference here when the numbers are positive? So when it's positive, sign magnitude 1's, 2's is the same. So again, for 1's and 2's, it's the same. Okay, what about minus 80? First, in order to represent it, so this is B, minus 80. Remember this guy. This is 110 in binary. In order to represent minus 80 in sign magnitude 1's and 2's complement, we should represent 80. So 80 is how much? I'm not going to use some division here. I'm just going to use this stuff. 80 in binary, in normal binary, this one here, is equal to 1010000. So we have 4, 5, 6, 7 characters. Okay. In sign and magnitude, this sign uses 1 bit. Since this is negative, I should put 1. That's why in sign and magnitude it's 1. Then I go with this guy. 1, 1, 0, 1, 0, 0, 0. What about in 1's complement? We should only what? Convert. Okay, but remember, we are using 8 bits. Let's emphasize it. We have only 8 bits to represent those numbers. We have here 4, 7 bits. So if we were going to use 8 bits, what should we put here in the beginning? For 80? 0, yes. For the sign and magnitude, it's okay. Why did we need this 0? Because first complement is actually this guy, 0, 1, 0, 1, 0, 0, 0, 0, complemented. Okay, and it is going to be 1, 0, 1, 0, 1, 1, 1, 1. What about 2's complement? It's going to be this one. 0, 1, 0, 1, 0, 0, 0, 0, complemented plus 1, which is this one, 1, 0, 1, 0. Let me add it directly. If I add 1 here, this is going to be 0. Then goes here 0, 0, 0. This is the one, okay? So I have 1, 0, 1, then all zeros. Okay? And remember those. Okay, for sign magnitude, first and 2's complement. Is everything correct? Let me check it. Sign magnitude is okay. Okay. Now our job is the following. This is A, this is B, this is C. I should find 110 in decimal minus 80 in binary. And you are going to see now why we use 2's complement. This is equal as saying 110 plus decimal minus 80. That's why, pay attention, always when you're dealing with subtraction in binary terms, you can, in computer you never have subtraction actually. Always you have addition. Addition and subtraction is the same. Because when you want to subtract something, you add it with the opposite of that number. This is it. So let me check how it works for the first case. Sign magnitude. So I'm adding 110 plus minus 80, which should be 30. Let us check whether it's the case. So 110 is this much. I'm writing 110. It's 0, 1, 1, 0. I have 1, 1, 1, 0 plus minus 80 in sign and magnitude is this much. So I'm writing it. 1, 1, 0, 1, and I have 4 zeros. 0, 0, 0, 0. I'm adding them. I have 0 here, 1 here, 1 here, 1 here, 1 here, 1 here. 1 and 1 is 0. Then I have 1 in mind. 1 and 1 is 0. and I have 1 here. But hey, I told you, I have only 8 bits. Okay? And I need 9 bits to represent this number, which is also, even if I have 9 bits, is going to be false because of this one. This one thing means that if I have the most significant bit as 1, it's negative. So is this a negative? No. This is called overflow, meaning I don't have enough of memory to represent my numbers. And this is mistake. Yeah, everything is done correctly, but this is a precision problem. I don't have enough of memory to represent my numbers. That's why this is overflow, and it doesn't work. Okay? If you convert it into something, those 8 bits are going to be saved in our memory. This gives what kind of value? Just tell me. It's 62. Because this is 0. This is 62 in decimal, meaning 110 plus minus 80 is 62, which is wrong. Let me check it with 1's complement. Okay, so with 1's, again, we have 110 plus minus 80. 110 is the same, so I'm writing 110 here, which is 0, 1, 1, 0, 1, 1, 1, 0, plus minus 80 in 1's complement, which is this one. So I have 1, 0, 1, 0, and I have 1, 1, 1, 1. Let me add them. What do I get? I have 1 here. 1 and 1 is how much? Come on, help me. It's 0. I have 1 in mind here. 1 and 1 and 1, it's 1. I have 1 in mind here. 1 and 1 and 1 and 1 is 1 here. I have 1 here. This one comes here. 1 and 1 is 0. 1 and 1 I have 0. 1 and 1, this is 0. I have again an overflow. Overflow means that this guy, we are saying to that, I'm sorry, I cannot save you. I don't have enough of memory. Let's see how much is this. This is a positive number. What is its value? Can you tell me? One, 2, 4, 8, 16. So, it's 29. But 110 minus 80, is that 29? No. So again, it's wrong. Let me write like with a red mark. This is wrong. Now, let's see with 3, 2's complement. Again, we have 110 in 2's complement, which is this guy. 0, 1, 1, 0. Then I have 1, 1, 1, 0. Plus minus 80 in 2's complement is this much. It is 1, 0, 1, 1, and I have 4 zeros. Is that correct? Yes or no? I think I forgot a 1 here. Yeah. So when I complemented everything, I got this one, and I added 1 in the end. 1 plus, no, I forgot a 0 actually. I have another 0 here, I'm sorry. So, okay, so this is 2's complement, okay? Let me write it. I have 0, 0, 0, 0. Let me add those numbers. 0 and 0 is 0. 1 and 0 is 1. 1 and 0 is 1. 1 and 0 is 1. 0 and 1 is 1. Then, okay, 0 and 1 is 1 and 1 is 0. I have 1 in mind. 1 and 1 is 0. 1 in mind. 1 and 1 is 0. I have 1 here. Do I have overflow? Yes, I have an overflow. Is the number correct here or not? Check it and tell me. How much is this? It's 30. And how much is 110 minus 80? It's 30. Do you see why we use 2's complement? Even though we have an overflow, the result is correct. Why did we get the correct result? Because remember, 2's complement was 1's complement plus 1. So this 21, when we add 1 here, becomes 30. And it works. It might look strange, and I'm not going to explain to you why it works, because this needs a lot of time and concentration. If you want to understand the fundamental principles why it works, you should stay in a calm place, take a piece of paper and work on it and see why it works. Okay? Not with big numbers, with small numbers. And the precision should not be 8 bits, let it be 4 bits. And try it. Okay? So this is why the computers use 2's complement to represent the numbers. Even though we have an overflow, the result is correct. Any question? Okay.